This is Donna Nelson at the University of Oklahoma. I'm taping a lecture for my organic chemistry class. This is the second and final lecture for the chapter on acids and bases. And we are using David Klein's textbook, Organic Chemistry, Chapter 3, Acids and Bases. So we're continuing the first lecture, and this will be the second and final lecture for this chapter. So let's look at what we're going to cover. The position of equilibrium and choice of reagents, the leveling effect, which also can be thought of as a limiting effect, solvating effects of certain compounds, counter ions, and then Lewis acids and bases, in order to give another explanation to acids and bases other than the Bronsted-Lowry acidity and basicity. So let's get started on this. Choosing a reagent. An important skill is to be able to recognize, to choose an appropriate reagent for an acid-base reaction. Choose an acid from table 3.1 or the table inside the textbook's front cover, which is going to be provided to you in a separate file. You can look for it in the same place that you found these videos, which I am creating, as you see, that could effectively protonate each of the following molecules. And that means, what that means is, for each one, take these one by one, identify the molecule's conjugate acid in that table, and then, staying in that same table, find the conjugate acid in that table and note its pKa. Then, moving up in the table to the molecules that have lower pKa's, choose an acid above that one that you selected in the table. That acid will have a lower pKa. That means that it would effectively protonate that anion. And so you do that for each one of these, just as a little exercise. I don't think this exercise is given any place in your textbook, but it's a very simple exercise, and it's a good one to sort of get you started and get you comfortable with using that table and using this terminology. So do each one. You could even pause the video and do that now before we go on. Another important skill is to be able to choose an appropriate solvent for an acid-base reaction. The solvent should be able to surround the reactants and facilitate their collisions without itself reacting. So the solvent needs to be inert towards the reactants. Because water can act as an acid or base, it has a leveling effect, or you could think of it as a limiting effect on strong acids and bases. Acids stronger than the hydronium ion are not effective in water. Bases stronger than hydroxide are not effective in water. And so you might ask why, and that is because acids stronger than hydronium, instead of protonating whatever it is, whatever reactant you want it to protonate, it will simply protonate water and give you hydronium. Or if you're running a reaction under basic conditions, then when you add the base, if it is a stronger base than hydroxide, instead of attacking the reactant that you want it to attack, it will simply attack water. And so you'll have hydroxide present. So instead of adding that other stronger base and trying to get it to carry out a different reaction, you may as well just add hydroxide, because that's what you're going to have. Okay, so let's that's sort of the introduction. Let's look at some more of this. So the leveling effect, which another way to think of it as limiting effect. If you look up limiting effect, you won't find it. If you look up leveling effect, you'll find that. But you might look at it and think, leveling effect, what does that mean? So think of it as limiting effect. And here you'll be able to see it on this table. This table is 3.1, straight out of your textbook. And so acids stronger than hydronium are not effective in water. So here that is, and here is the line that separates hydronium from the acids that are stronger than H3O plus. Okay, they have a lower pKa. Also, bases stronger than hydroxide. So that means those below hydroxide in this table are not effective in water. That means because if you carry out try to carry out a reaction under basic conditions, and you're trying to have a base attack a certain reactant in water, when you put this in, it will simply deprotonate the water and you'll have hydroxide. Okay, so the reaction may still go ahead, but it will go ahead. This will be the active base. So the range is identifiable in the table below. So these, you can add them, they just won't be effective because this is what you'll actually have in solution. This is if you carry out the reaction, if you're trying to carry out the reaction under basic conditions. If you're trying to carry out the reaction under acidic conditions, then of course you would add an acid. And so if it's an acid that's stronger than this, then the acid will simply protonate to water and you won't have that acid present. You'll have the hydronium. So I hope this little picture here, this little diagram, explains it because it seems to be a little bit confusing to me. So I hope that helps. That is beyond, that explanation is beyond what you see in the textbook. Water is appropriate as a solvent when the base is not stronger than hydroxide. So here we're trying to carry out the reaction under basic conditions. When you see anions, that means the reaction is carried out under basic conditions. And if you add an acid to this, you'll simply neutralize the reaction. So this reaction is being carried out under basic conditions. Water is appropriate as a solvent when the base is not stronger than hydroxide. And this base is not going to be stronger than hydroxide. Okay, so here you can see that this is going to deprotonate water and give this these products. And so this is an equilibrium. The pKa here, this is 15.7. The pKa over here is 4.75. This is obviously a much stronger acid. This is going to be a weaker base. This base is weaker than hydroxide. So this should be okay. That means that the reaction will lie to the left. So the pKa, that tells you that this is a stronger acid. It has a lower pKa. This is a weaker acid. This has a higher pKa. And so the reaction is going to lie to the left. That tells you that when acetate is used in a solution of water, that's okay. You won't have a conflict there. And because the equilibrium will lie to the left, so you will still have sufficient acetate that it will be available for reaction instead of hydroxide. And so water would be an appropriate solvent here, but it's not always. I think there's an example. Yeah, here's an example of when it's not. So notice that was under basic conditions. You saw anions. This is under acidic conditions. And so here we have an acid, and you see the hydronium ion. So what we have here is sulfuric acid, which you know is a strong acid. It's protonating water. You have hydronium. Here is the bisulfate anion. This is the acid, this is the conjugate base, this is the acid, that's its conjugate base. So acids stronger than hydronium are not effective. This is not effective in water. So, for example, what happens here is that this is such a strong acid. Look at the difference here. It's 7 pKa values. That's too great a difference. And so this equilibrium is going to lie far to the right. This sulfuric acid is really going to protonate water, and you're going to have mostly hydronium, very little sulfuric acid. And so even though sulfuric acid has been added to the water, no sulfuric acid effectively exists anymore. This is the acid that exists. And so this is what will be available to carry out the reaction. So there is that limiting effect. It's called a leveling effect in your textbook. And when you read leveling effect, perhaps it might help if you think of limiting effect, because it limits the acids and bases that can be used because of the reactivity of water to pick up a proton or to lose a proton. Here's another example of leveling effect, and this is not on our table, on the table 3.1. You'll have to go to the table that exists in the front of, on the back side of your cover page, the textbook cover page, to find these molecules. And this one in particular, I think this one is in table 3.1. But anyway, you'll be able to find these and you'll be able to compare them. And so bases stronger than hydroxide cannot be used in water. For example, we wouldn't be able to perform this acid-base reaction in water. Why not? Because this is a very strong base. And this would simply abstract a proton from the water, and so it would be protonated. You would not have any of this present. Okay, you would have this and hydroxide, and so this reaction would not be possible. You would not be able to achieve or study this reaction in water. So you might want to look these values up on the inside of your front cover, the table for pKa's, and convince yourself of that. Figure that out and understand it. Because they are so similar, the areo can't be used to explain the pKa difference comparing ethanol and T-butanol. Notice ethanol has a pKa of 16, tert-butanol has a pKa of 18, and so that tells you that ethanol is about 100 times more acidic than T-butanol. So the only difference, notice, is the size of the alkyl group. The size of the alkyl group is the only difference here. And so you have to think about the difference in the stabilities of the conjugate bases. That's where the reactivity and the actual acidity, the stability of the bases, that's where that lies. And so you have to think about the abilities of solvents to stabilize these conjugate bases. And so we'll look at that on the next slide. But before we go to the next slide, there is something that I want to say about this areo. Areo, remember this is atom, resonance, induction, and orbital. And so that is telling you the effects, the stabilizing effects, these 4 stabilizing effects up on anions in descending order. So the effect of the electron pair lying on a particular atom has the greatest effect, and the orbital that the lone pair resides in has the lowest effect in these 4 criteria. And so I want to say it's not given to you here, but it will be given to you later on, and it will become very important later on in Chapter 7, the solvent effects. Solvent effects are so powerful that they can override all of these. Okay, so solvent effects, if you have to list the solvent effects in with these, it will be the strongest. Okay, it can outweigh any of these, all of these. However, the solvent effects are so different. It's not just stabilizing the negative charge the way that you can think of it and easily compare here, but it is still a stabilizing effect, but it's actually what we call a steric effect. It is due to the size of the alkyl group and how difficult or easy it is for the solvent to reach the negative charge. And so I'll show you that. But just remember, solvent effects goes right along with these, except they're not explained quite the same, and they are more powerful. Okay? And carry that information with you straight through to Chapter 7 because you're going to need it. You will use it a lot in Chapter 7. So don't just think that you're going to be able to learn this and then forget it for the next chapter, because you'll be using this for the rest of organic chemistry. This is a very important concept, this REO and also solvent effects. So let's look at this next slide. The solvent must form ion dipole attractions to stabilize the negative charge. So here is the anion. Here is the other anion. These two anions were formed from the two alcohols that you saw on the previous transparency. And you can see the pairs of electrons on oxygen. You don't see the negative charge, but it's there. Okay, you'll just have to take my word for it. This is negatively charged. This oxygen is bearing a negative charge. So is this oxygen bearing a negative charge. And this is an electrostatic potential map. This is the same as that, except that is a bond line diagram. This is a bond line diagram. This is an electrostatic map of that. So here you can see the red ball here. That is oxygen. And you can see the 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. So this molecule is that molecule depicted in a different way. Over here, this molecule is an electrostatic diagram showing ethoxide. They are the same. This one is just a bond line notation. This one is depicted in a different way. This shows where the concentration of electron density is. This is oxygen. Note that it's red. That indicates that most of the electron density is concentrated on oxygen. Just like over here, most of the electron density is concentrated on oxygen. These two look very much alike. You can see the oxygen, you can see the red surrounding the oxygen, you can see carbons, you can see the blue surrounding the carbons, etc. They're very much alike, as you would expect, because that's alkoxide, this is alkoxide. They are both oxygen with an alkyl group attached. So the important part comes, the difference comes when solvent needs to come in and form ion dipole attractions. These ion dipole attractions, which we looked at in Chapter 2, will be what what stabilizes the anion, and it will stabilize this anion. And so basically, this is bearing a negative charge, this is bearing a negative charge, it's ethoxide. The ide tells you it's an anion. So this is an anion, the negative charge is here. This is an anion, the negative charge is here. basically, the most simple way to think of this is that anion, remember what I told you about spreading the charge out, stabilizes it. Whether it's a cation or an anion or a radical, spreading out the negative charge or spreading out the positive charge or spreading out the unpaired electron density by any method, whether it is resonance or induction or the solvent effect, which is what's going on here, it stabilizes that ion. So what's happening here is the solvent comes in and it gets close to this ion. It gets close to that negative charge. And so what happens is this negative charge polarizes that solvent. So the solvent, if this is partially negative, which it is because it's bearing a negative charge, this molecule is bearing a negative charge. I, that tells you it's an anion, so it's bearing a negative charge. When the solvent comes in and gets close to the anion, the solvent will become polarized in the presence of that anion. So this solvent, I don't know what the solvent is, whatever it is, it will become polarized. One end of it or one part of it that's close to this pair of electrons on oxygen will become partially positive, and the other end will become partially negative. This one will become partially positive, and the other end partially negative. This end will become partially positive. The other end will become partially negative. So what you have is a negative charge which is stabilized by these ion dipole interactions where you have partially positive, partially negative, partially positive, partially negative, partially positive, partially negative. And when those molecules that are capable of creating these dipoles come in and get close to it, the negative charge is effectively borne out here on the ends of these solvents. So that means that the negative charge is spread out instead of being focused just on that one atom. Now it's spread out. Part of it's residing out here. This is partially negative, partially negative, partially negative. And so you've spread out the negative charge. Anything that can be done to spread out a charge or unpaired electron density stabilizes that molecule. And so this molecule is stabilized when these solvents get up close to the center of negative charge. So this is ion dipole attractions. Stabilize the negative charge. And the same thing is going on over here. The only difference is that this has 3 alkyls, this has 1 alkyl and a couple of CH bonds. CH bonds are smaller than methyl groups. So this is a small CH bond, a larger, although methyl is small, a larger methyl group. Methyl is small, but it's larger than CH. So here, this has less bulkiness, more bulkiness. We also call that steric hindrance. Steric, S-T-E-R-I-C, hindrance. You can think of it. Steric hindrance, you can think of it as bulkiness. It means the same thing. So this is more bulky, less bulky. You can see the bulkiness here. You can see the lack of bulkiness here. So this part of the molecule is relatively free. Over here, you have a couple of methyls in that spot. So now, it has enough space to accommodate, say, 3 solvent molecules. It will differ depending on the size of the solvent molecules. Same thing over here. It will differ depending on the size of the solvent molecules. But in order to have a valid comparison, we have to use the same solvent in each reaction. You can't use a large solvent over here and a small one over here. You have to use the same solvent. When you're comparing a reaction or comparing an interaction, you change one thing at a time. So we're going to keep the same solvent, keep the same atom bearing the negative charge. The only thing we're changing is the bulkiness of the alkyl group. And so when the alkyl group is really bulky, you can get a smaller number of solvent molecules around the ion. When it is smaller, because this is just ethyl, you can get more solvent molecules around that ion. And the more solvent molecules that you have around the ion, the more dipoles you're going to have created in the solvent, and you're going to have more ion dipole attractions and interactions because you can get more solvent molecules around this oxygen that has less bulkiness attached to it. There will be a smaller number of solvent molecules that can crowd in to this O minus and stabilize it. So this O minus that has less bulkiness attached to it will be more stabilized, and this one will be less stabilized. And so that's why ethoxide is more stable than T-butoxide in, say, water. And so that means that when you have OH, it will be a better acid than when you have T-butyl OH, because the anion can be more stabilized in water. This is assuming that both of these are in water. So this is less, the corresponding alcohol is less acidic than the corresponding alcohol for that. And I hope that explained that. If not, you can ask questions about it in class, of course. So now, counter ions also can be spectator ions. What that means is, and they usually are, that means that they usually just sit there and do nothing. These are counter ions. Usually they're cations, say when, sodium. So sodium is an excellent example of the counter ion. So this is sodium amide. So the sodium amide will react with water. This will deprotonate water and give hydroxide. And so, however, when it's drawn, the reaction may be drawn, and since the sodium, Na+, the sodium cation, does not react, does not become involved, usually doesn't. Sometimes it can become important. Sometimes the counter ion can be important and make the difference in a reaction. Usually not. If it's not, then it's just simply ignored. There's no impact, and so it's just not drawn. To draw it every single time when it makes no difference would simply clutter up the reaction and draw your eye towards things that are unimportant. So the counter ions are often just omitted as they are here. In this case, they're just spectators. They don't get involved in the reaction. The Bronsted-Lowry acids and bases, instead of focusing on electron pairs like the Lewis acid definition, they focus on protons. Acids donate a proton, bases accept a proton. So you recall from this reaction from general chemistry, the HCl is donating a proton, and here's the conjugate acid that comes from HCl. This is the proton acceptor, and so this acid and base form this conjugate acid and base. HCl is donating the proton. The water is a base in the fact that it is accepting a proton, and so hydronium is the conjugate acid from water, and chloride is the conjugate base from hydrogen chloride. So now let's look at this discussion of Lewis acids and bases. The Lewis acid accepts a pair of electrons. Lewis base donates a pair of electrons. Acids under Bronsted-Lowry definition are also acids under the Lewis definition. So bases under the Bronsted-Lowry definition are also bases under the Lewis definition. So this reaction fits both definitions. Here, once again, it's the same reaction that you saw on the previous slide. We have water deprotonating HCl, you have hydronium and chloride. This is exactly what you saw as before, except instead of focusing on the proton, now we're focusing on the pair of electrons. The pair of electrons pick up the proton. Here the pair of electrons move back onto chloride. And so now you have the water bearing a proton, which is hydronium, and this HCl has lost a proton. So now we're focusing on the Bronsted-Lowry definition. But this reaction can fit either definition. Now here's a reaction that does not fit the Bronsted-Lowry definition because there's no protons involved. If there are no protons involved, the Lewis acid and base definition must be used. So here we have a pair of electrons attacking the empty p orbital on boron. The oxygen-boron bond is formed. Boron will bear a negative charge because it has accepted this pair of electrons from oxygen. Oxygen bears a positive charge because it has donated a pair of electrons. This oxygen-boron bond, if you want to think of which atom owns those electrons, there are 2 electrons in that bond. Oxygen owns one of those 2 electrons, and boron owns one of those 2 electrons. Hence, boron has picked up an electron, that's why it bears a negative charge, and oxygen has given up an electron, and that's why it bears the positive charge. So, this is the end of the discussion of acids and bases from chapter 3, and you should have learned a lot of good material here, and some of this material is going to be extremely important to you later on. You will desperately need it in chapter 7, where we consider nucleophilic reactions, reactions of nucleophiles and electrophiles. You will need it greatly there. I urge you to learn this now so that later on you will be able to focus on other things which are extremely important, and you will not have to come back at that point and learn this material. So if you have any questions, please ask them in class.